Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Model Part 6 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand number 1, the basics of shell model, number 2, knowledge of magic numbers in nuclei, number 3, finer details of the shell structure in nuclei. Nuclear shell model, wood section potential. In this particular slide, we are going to study the nuclear shell potential when we have assumed the wood section potential. So here the form of the wood section potential is given that Vr is equal to minus V0 1 upon 1 plus e to the power R minus capital R upon A, where the symbols have been defined in the picture given below. And on the right hand side, the energy level distribution is given in terms of increasing energy. That is, if we move from top to bottom, from bottom to top, the energy of the levels increase. So here, basically the first 1p state is the first state with L is equal to 1. And level degeneracy is basically 2L plus 1. So what we finally can see that even if we apply the wood section potential, even if we consider the wood section potential and solve the quantum mechanical problem for that nucleus, we can basically reproduce only the first 3 magic numbers, that is 2, 8 and 20, whereas the other magic numbers cannot be reproduced. Nuclear shell model, wood section potential. So in this slide, basically we are going to compare what we have obtained as the solution of Schrödinger wave equation when we have considered 3 nuclear potential, that is harmonic oscillator potential, wood section potential and square well potential. So in this slide, basically for all 3 kinds of potential, the energy states are being shown and the number of nucleons, that is number of neutrons or protons filled at these energy states are also shown. For example, in the first state only 2 nucleons are possible, in the that is 1s state only 2 nucleons are there, in 1p state 6 nucleons are there, that is up to the second state we have 8 number of nucleons. Then at the third energy state we have 2s and 1d, which corresponds to 12 nucleons to the maximum capacity. So up to the third state 20 nucleons are there, and likewise the higher states. In case of wood section potential, the similar situation is there, that is up to the first state 2 nucleons, up to the second state 8 nucleon, up to the, since the third and fourth state are very close, so here we can say that the 20 nucleons are there, and likewise. Similarly, the situation for a square well. So what we observe, what we can conclude out of this slide is that in all 3 potentials, the solution of the Schrödinger wave equation gives you only the first 3 magic numbers, that is 2, 8 and 20. So it means if we consider harmonic oscillator potential or wood section potential or a square well potential, the solution of the Schrödinger wave equation for nuclear potential basically can explain the origin of first 3 magic numbers, that is 2, 8 and 20, whereas the higher magic numbers are not reproduced. It shows that there is something missing in this interpretation of the nuclear shell model, that not only the mean field potential like harmonic oscillator, square well or wood section is there, but there has to be something else which need to be included in this potential, which can give us the higher magic numbers also. Nuclear shell model, spin-orbit interaction. So in this slide, basically a new kind of interaction is basically discussed, and this interaction is also within the nuclear domain, so it will also has influence in filling the various nuclear energy orbits. In nuclei, the spin orbit effect comes from the nuclear surfaces. As for the nucleons other than on the surface, the strong spin direction forces are balanced due to same environment around them. What does that mean? That in the picture shown here, the inner nucleons find themselves in an identical environment of nucleons around them, but the nucleons which are on the surface, they found many number of nucleons, many number of surrounding nucleons from inside, but nothing from outside. So it means the nucleons which are on the surface of the nucleus, there is slightly imbalance of the forces. So that imbalance of forces is nothing but in terms of spin orbit interaction. So now spin orbit interaction means, since we know that nucleons have spin, angular momentum, that is, which is called the intrinsic spin, and nucleons are in motion in the mean field potential. So there is basically, due to the orbital motion of the nucleons, there is a mean field or there is a magnetic field inside the nucleus, and in this magnetic field the nuclear spin basically interacts. So it's an interaction between the intrinsic spin of the nucleons in the magnetic field provided by the orbital motion of the nucleons. So that is why the name is spin orbit interaction. Now when we worked out the energy corresponding to this spin orbit interaction, then it turns out that energy is given by ESO is equal to h bar c whole square upon mc square whole square into 1 by r dvc over dr L dot s, that is W atom R into L dot s. So this expression is for atoms. So in case of atoms also, this interaction is there, and originally it was, since this spin orbit interaction was defined to explain the fine structure of atom. So similar concept is basically adopted in case of nucleus also. So here in this case basically the charge carriers are basically electrons, whereas in case of nucleus the charge carriers are protons, where neutrons are neutral. So we can say that the spin orbit interaction in case of nucleus is of opposite sign as compared to the case of atoms. Nuclear shell model, spin orbit interaction. So here in this slide basically the details of spin orbit interactions are being discussed. Here in the left hand side picture, the spin orientation of intrinsic spin S and orbital angular momentum L are given, and the direction of magnetic field is also given. So here basically when the spin and orbital angular momentum, they are directed upwards, then in that case the J precesses around the direction of magnetic vector, that is direction about the direction of magnetic field. Whereas in the other case, when L is pointed down and S is up, so it means L and S both are not in the same direction, then J basically again precesses around the magnetic quantum number axis or the magnetic field. So it results in a different kind of energy. So the two different states of orientation of orbital and spin angular momentum result in two different cases. When they are parallel, when L and S are in the same direction, it is called stretch case, that is J is equal to L plus half. It is the low energy state. Whereas in the other case, when S and L are in different direction, it is called jackknife case, where J is equal to L minus half, and it is called the high energy state. So here basically if we represent them in terms of energy, then a single, in the absence of spin orbit interaction, there is only one energy state, but when we incorporate the spin orbit interaction, the single energy state is basically split into two. The lower state defines the situation when L and S are basically in the same direction, whereas the upper state defines the situation when L and S are not in the same direction. So the energy separation of the two states from the original energy is basically called the energy splitting. So it is represented by delta E. So delta E Ls is equal to EJL plus half minus EJL minus half is equal to mean value of ULS L plus half, and the figure shown is that we can find an expression for delta E LS. Nuclear shell model, spin orbit interaction. Now in this slide, basically we are going to introduce another kind of interaction, which is the spin orbit interaction. The nuclear potential with a spin orbit term is V, which is a function of small r L dot S, is equal to VR plus VLS r L dot S. What does this mean? That if we consider the spin orbit interaction for the nucleons while they are in motion inside the nucleus, then our net potential becomes VR, which is the central potential, plus, or which is basically the mean potential, plus the potential corresponding to the spin orbit interaction. So in the previous cases, when we have assumed only the Bode section potential, harmonic oscillator potential and square wave potential, in all three cases only a single potential was assumed. But now with the introduction of a spin orbit interaction, if we assume that a spin orbit interaction also exists among the nucleons, then our potential is modified, the mean potential is modified, and the total potential inside the nucleus is now given by this expression. The spin orbit term make the nuclear potential well wider for nucleons with a spin parallel to the orbital angular momentum and less wide for nucleons with a spin opposite to the orbital angular momentum. So what does that mean? That with the introduction of a spin orbit interaction, first of all, since we know that what is a spin orbit interaction, it is an interaction between the nuclear spin or the spin of the nucleons and the angular momentum or generated due to the circular motion of the nucleons in the mean field. So it's an interaction between these two. So when the spin and orbital angular momentum are having the parallel value are parallel, in that case the spin orbit interaction term make the nuclear potential well wider. But when the nuclear spin and orbital angular momentum are antiparallel, in that case the spin orbit interaction term makes the nuclear potential less wide. So it means in this case, due to the spin orbit interaction, in the Wood section potential, if we consider, in the Wood section potential the form was like this, but due to the spin orbit interaction and the two nature of a spin orbit interaction, we have, instead of single curve, we have two different curves. One corresponding to L and S both are parallel, and another one corresponding to L and S antiparallel. The wider well, which is the result of L and S parallel, results in states of lower energy. Without a spin orbit interaction term, the energy of a state does not depend upon the total angular momentum. Nuclear shell model is spin orbit interaction. Now in this slide, the impact of a spin orbit interaction on the energy levels or the nuclear potential is being discussed. So the two pictures are given. In the left hand side, it shows the proton potential well as a function of distance from the center of the nucleus, and the Coulombic repulsion term is also given. So here from this picture we conclude that the neutron potential well is deeper than the proton potential well, and the reason is understood because the protons have Coulombic repulsion also. So Coulombic repulsion is basically, we can say that basically the resultant proton potential is the result of the nucleon potential minus Coulombic repulsion. So this is the normal situation in a nucleus, but when we add the spin orbit interaction term, then what happens? For example, if we see that if we take the neutron potential well, Then in the neutron potential well, with the inclusion of spin-orbit interaction for spins opposite to orbital when S and L are in different directions, we find that the potential well become thinner. That is, the width of the potential well decreases. But when the spin and orbit angular momentum are in the same direction, then it results the little bit of expansion of width of the nuclear potential. So it means, depending upon the nature of spins of intrinsic spin angular momentum and orbital angular momentum, we have two different situations. Corresponding to L minus S, we have the width of the nuclear potential smaller. Corresponding to L plus S situation, we have the width of the nuclear potential expanded as compared to when there was, compared to the case when there was no spin-orbit interaction. Nuclear shell model with spin-orbit interaction term. So now in this slide, we are going to discuss the overall impact of spin-orbit interaction in the nuclear potential. So when we add this spin-orbit interaction with the nuclear interaction, what is the situation? We have the net potential is equal to half m omega 0 square r square, which is the harmonic oscillator potential, plus C L dot S, where L dot S is the spin-orbit interaction potential, plus dl square. So it means the nuclear potential, the resultant nuclear potential consists of three terms. First term is the harmonic oscillator potential, second term is the spin-orbit interaction potential, and third term is basically a correction factor which gives you the flattening of nuclear potential at the center. Now when we use this resultant potential and solve the Schrodinger wave equation, our energy levels, the eigenvalue of that situation comes as ENL is equal to h bar omega 0 2NL 2n plus L plus 3 by 2 plus d L into L plus 1 plus C epsilon spin orbit. So it means we see that the energy levels are not just single energy level, single or isolated energy levels, but there is degeneracy in the energy level corresponding to different values of L. So here we can see that in the absence of potential, in the absence of spin orbit interaction, we have the energy situation as 1s, 1p, 1d, 2s, 1f, 2p, 1g, 2d, 3s, 1h, 2f, 3p. But with the spin orbit interaction term, each of these levels other than S level is basically splitted into number of components, into two components, one corresponding to L plus S, another one corresponding to L minus S. So we observe that instead of single isolated levels, due to the spin orbit interaction, we have large number of levels, and these levels basically have been named as per their L plus S or L minus S value. If we start filling these orbits from the bottom to the top, we find that in the first orbit we can accommodate only two nucleons because they are neutron proton are fermionic particles. So Pauli exclusion principle will be applicable, and as per Pauli exclusion principle, in the s orbital we can accommodate only two nucleons. In the second nucleon we have p3 by 2 and p1 by 2. So up to the second level we have 8. Then up to the third level we have d level and s level. So d5 by 2, d3 by 2 and 2s half. So in this up to third level we have 20. In the fourth level we have an isolated f7 by 2 level. So up to the fourth level we have 28 number of nucleons. Then fifth, sixth, seventh. So in that way we can say that we have obtained all the magic numbers, that is 2, 8, 20, 28, 50, 82 and 126. So you can see that just by adding a small correction term like a spin orbit interaction, our solution of Schrodinger wave equation basically results in all the magic numbers. So this seems to be a complete potential in itself, as we could explain the origin of various magic numbers in nuclei. Nuclear shell model applications, spin and parity. So now in this slide basically we come to the application part of nuclear shell model, that how the nuclear shell model can explain the ground state spin and parities in nuclei. Shell model can be used to predict the ground state spin and parity of the nuclei. For odd A nuclei, the angular momentum, which is basically the spin, is determined by the angular momentum of the last nucleon in the species, that is proton or neutron, that is odd. So suppose we have an odd A nucleus, then odd A nucleus can be assumed as equal to an even nucleus plus the lone particle. For example, if we talk about oxygen 17, oxygen 17 is basically an odd A nucleus. So oxygen 17 can be assumed as equivalent to oxygen 16 plus 1 neutron. So in that case, the oxygen 16 nucleus is basically even nucleus, so its total spin is 0 as per the Pauli exclusion principle, plus since it has got the lone proton or a single neutron, this neutron, whatever is the spin of this neutron, will be the spin of odd A nucleus. In even A nucleus, for even nuclei, the ground state always has spin 0, net angular momentum associated with even n and even z is 0, and parity is positive. Because since why the spin is 0? Because all the nucleons in the even nuclei are paired up. So one is spin up, one is spin down, so total spin is 0. So if we add all the spins, result is 0. So in case of even nuclei, the ground state spin is always 0. Now what about the parity? Parity is defined as minus 1 to the power L. So here basically, since the L value is also 0, so it means in net L value is also 0. So it means in this case, the parity is positive. So ground state spin and parity is 0 plus. Nuclear shell model applications, spin and parity. So up to the previous slides, we have seen that how shell model was developed and how the various magic numbers are obtained out of theoretical treatment. Now we are going to apply the shell model to explain various experimentally observed ground state properties of nuclei. So in this slide basically we are going to explain the observed spin and parity of various nuclei in their ground state. In even A nuclei, for odd nuclei, the last neutron couples to the last proton with their intrinsic spins in parallel orientation. What does that mean? It means that in even A nucleus means when there is an odd nuclei, for odd nuclei, the last neutron coupled to the last proton, their spins are parallel, so they can couple. In odd A nuclei, the total spin and parity determined by the single nucleon. It means in odd A nuclei, we can consider at even nuclei plus an odd nucleon. For even nuclei, the resultant spin is 0, whereas for the odd nucleon or the lone nucleon, total spin and parity is basically defined by that spin and parity of that nucleon. There are exceptions to this rule. Example, oxygen 17, I5 is equal to 5 by 2 plus. So there are exceptions, as we can see that in case of oxygen 17, the neutron is odd, so the spin value obtained is 5 by 2 plus. 2 closed shell for protons and neutrons plus 1 unpaired neutron. Nuclear shell model applications, spin and parity. So we continue our discussion about how the spin and parity values in various nuclei can be explained with the help of shell model. So here in this slide, basically the energy levels of oxygen 17 are being plotted for protons and neutrons. Number of protons in oxygen 17 are 8, number of neutrons in oxygen 17 are 9. So it means in this case, this is an odd nucleus where neutron number is odd. So here it means the spin and parity as per the shell model, the spin and parity of oxygen 17 should be decided by the spin and parity of the 9th neutron. that in which orbital this ninth neutron will be. So here in the picture we can see that the ninth neutron will occupy d phi by 2 state because it is lower in energy as compared to the 2s state. So it occupies the d phi by 2 state. Therefore, the spin of ground state spin of this nucleus is 5 by 2, and since d is positive, so parity is positive. So I pi is equal to 5 by 2 plus. So neutron configuration is 1s half square 1p 3 by 2 to the power 4. It means 1s half can accommodate 2, 1p 3 by 2 can accommodate 4 number of nucleons, and 1p half can accommodate 2. In case of neutron, 1s half can accommodate 2, 1p 3 by 2 can accommodate 4, 1p half can accommodate 2, and then 1d half, 1d 5 by 2 can accommodate 1. So here we can see that with the help of shell model, we can explain the spin and parity of oxygen 17. Nuclear shell model applications, spin and parity. So in the previous slide, we have understood how the nucleons are distributed, how the protons and neutrons are distributed in oxygen 17. Here in this slide, we are comparing the two cases, that is the cases of 15 oxygen and 17 oxygen. In 15 oxygen, the number of neutrons are 1 less than what is satisfied for stability. That is, ideally in oxygen 16, which is the stable nucleus, we have 8 protons and 8 neutrons, both are magic. Whereas in case of 15 oxygen, we have 8 protons and 7 neutrons. Similarly, in case of oxygen 17, we have 8 protons and 9 neutrons. So in one of the two nucleus, there is one vacancy, whereas in the 17 oxygen case, there is an added nucleon outside the closed shell. And here we can clearly see that by the distribution of protons and neutrons in these energy levels, we can basically determine the spin of oxygen 15 and oxygen 17. In case of oxygen 15, there is one hole in p half, whereas in case of oxygen 17, there is one particle in d 5 by 2. So it means for oxygen 15, the ground state spin is 1 by 2 plus, whereas in case of oxygen 15, the spin and parity is decided by the odd neutron, which is in the d 5 by 2 orbit. Nuclear shell model applications, spin and parity. Now in this slide, we can basically see what are the ground state spin and parity of the nuclei. For example, in lithium 7, the ground state parity and spin and parity is 3 by 2 minus. For beryllium 9, the ground state spin and parity is 3 by 2 minus. For calcium 40, it is 0 plus, and so on. So looking at the number of protons and neutrons in a given nucleus, we can identify the ground state spin and parity in the nucleus. So students, let us summarize what we have learned in this module. We have discussed so many concepts, but what is the ultimate gain we have? We have learned, number 1, experimentally, Wood section potential is found as the most realistic potential. Second thing what we have learned is spin-orbit interaction is crucial in producing nuclear magic numbers. Third thing that we have learned is that sign of spin-orbit interaction term in nuclei is opposite to that in atoms. Next thing which we have learned is that spin-orbit interaction changes the width of nuclear potential. And finally, shell model can predict the ground state properties in nuclei well.